Welcome back to the second part of lecture number 14. We have been discussing about the deformation processing, and part 1 of the lecture I was discussing about the effect of strain rate. And you can see the values of strain rate starting from tensile testing to about explosive forming, how the strain rate can be changed order of magnitude. And these are all used: hydraulic sprays, mechanical sprays, forging hammer, explosive forming things are used in real metalworking industry, in automobile industry also. So therefore, we should have some idea about these things. So flow stress is always a function of temperature and strain rate. You have to understand that. And it has been found that as the strain rate increases, the resistance to deformation increases, and this effect is known as a strain rate sensitivity. How it will depend on? Well, strain rate sensitivity is calculated using this equation. I already shown you that sigma t is equal to C epsilon dot to the power m, where m is the strain rate sensitivity. M is the strain rate sensitivity. So this is how the flow stress. This is flow stress. This is your strain rate. And C is a constant, and M, as I told you, is strain rate sensitivity. So depending on the value of M, this flow stress will change, and M is a very important parameter. How do you find M? Very simple. You can take log on both sides. So if you take a log on both sides, what happens? Very simple. It basically gives you this equation, which is a straight line equation. Now if I plot, I am doing it here, show you the next slide. Log sigma t on the y axis and log epsilon on the x axis, I should get a straight line with the intercept given by log of c, and slope of this curve will be m. So therefore, you can easily measure m, and m is basically material property or material parameter. This is what is done here. You can see that. So on the right side we are plotting log, on the left side we are plotting without log. So log you get simply a straight line, and the straight line value is, you can see that at strain rate of 10^1, the value of C is this. Okay, let me show by other color. Value of C is this. Why it is not changing? Let me see why. Okay, it should change now. This is the C value. This is the value of strain rate, right? Now slope of this curve is m. Very easily you can obtain that. So this is the equation I told you. This is the fundamental equation. Remember, I told you that. Okay, these are the equation you will require when you want to do machine learning based modeling here. And it has been found that as you increase the temperature, the flow stress, dependence of the flow state with the strain rate, it basically becomes very pertinent. At room temperature, strain rate does not make much difference. Only at high temperature, strain rate make difference. So you can see that opposite trend, right? If you increase high temperature, yield stress decreases, ductility increases. You can deform the material easily. But if you want to deform at a faster rate, you have to apply more stress at high temperature. That is why the cold working is sometimes useful. At cold working, you can deform at any rate you want, because it does not depend on the strain rate, the flow stress, right? But at hot working conditions, flow stress is strongly dependent on the strain rate. So in hot working condition, you cannot apply beyond a certain strain rate. Therefore, your production ability or the productivity of the plant cannot be changed. But in cold working condition, you can actually apply any strain rate you want. Obviously, you should not apply very high strain rate, so the material becomes cracked or failed very easily. So this is the main reason actually why cold working is many cases useful. Now I do not want to much spend on time on this. Basically, is talking about how the C and M can affect the material behavior. Now I will little bit talk about another factor, what is called friction in metal forming. In the most of the metal forming processes, you are using die. and not only that, you are using moving components, and when the moving components are used, there will be always friction and metal flow is retarded. Like here, a workpiece is pushed through a die. So, in between the contact points between this workpiece and the die, there is going to be huge amount of friction, and friction and tool wear are more severe in hot working conditions. And because of this, metal flow is retarded, forces and power are increased, and it can lead to lot of wear and tear of the tool. So, one must take care of this, right, because this will also affect your productivity. If the dies are getting worn out very easily, you can understand what will happen. So, metal working lubricants are applied to tool work interfaces, and they can reduce the forces sticking, power, tool wear. They can give better surface finish, and it can even remove heat from the tooling, because of friction there is a lot of heat also produced. And when you choose a lubricant, this is also very important exercise using machine learning. What kind of lubricants will be best for your operation? I know it depends on type of forming process, rolling, forging, sheet metal forking, etching, whether it is hot working or cold working. Obviously, some lubricant may work at room temperature, may not work at high temperatures. What kind of work material you are using, chemical reactivity of the tool with the work materials in presence of the lubricant, and obviously cost and ease of application is also a factor. So, as you see, in cold working condition you can use mineral oils, fats, fatty oils, even soaps or water based emulsion can be used, because they will not affect much at room temperature. But hot working condition you can use only two things, molten glass or graphite. Okay, remember that. So, you have a limited choice at high temperature. That is why hot working is more difficult, cold working is easy. Now, I have given you a perspectives of different parameters which are required. I talked about different processes like loading, forging, extrusion. Let me switch the gear, because we have to move little fast, otherwise we cannot catch up with the statistical and machine learning based tools as quickly as possible, for which many of you are actually waiting for. So, now we can also use a technique called powder processing or particular processing of metals and ceramics. So, deformation processing is widely used for metals or alloys, but this one can be used for both metals and ceramics. What is done here? You take a powder of any material. I give an example of tungsten, right? Blend it or mix it. Basically, blending mixing means making it proper, and after that you put in a die, compact it. Compacting is to make a component of the shape you want in a green way. Green way means what? You have the strength between the particles are loose particles are very low. Then you have to make it strong, compact. You have to sinter it high temperature. High temperature allows the diffusion of atoms to happen, and that can lead to good sinter products. This is in a nutshell the whole process is. So, one slide we can describe the whole process is, but there are so many ifs and buts or conditions. So, in a powder metallurgy you must know your powders very well. That is why this characterization of engineering powders are very important. Size, shape, how they are, when you pour it, what is the angle of inclination they produce, and obviously you should also know production of metallic powders. I do not think I can discuss everything here, and then important aspect is the pressing and sintering. And there are many alternative sintering processes available. You know that lot of advancement happen in terms of the processing of these powders. So, what is powder metallurgy? Nothing but a metal processing technology in which parts are produced for metallic or ceramic powders. So, there are two sequences important. One is the pressing of powders. Their powders actually compressed into a shape, desired shape, to produce green compact. Green, remember this word green compact, because bond between the powder particles are very weak, and this is accomplished in a press with punch and dies designed for the parts. You can create a die of shape you want, and then you can use punch to push the powder, and after these green compact are prepared, they sinter. Okay, the sintered are heated up to high temperature to bond the particles into a hard rigid mass. This is performed normally high temperature, below the melting point of the material. So, why it is important? Because there are many materials on which you cannot either cast or you cannot deform processing by deformation. What will do? Like let us take about tungsten, pure tungsten. I can't do anything. Tungsten is a very high melting temperature, 3400 degrees Celsius temperature, and it cannot be melted, it cannot be cast very easily, and it is very difficult to deform, because as you understand Tm by 2 for tungsten is how much? Let us do the calculation. So, W is tungsten, right. Tm is assume Tm of tungsten is 3400 degrees Celsius. Let us assume that, although it will be much higher, I understand, but not very high form. So, this is Tm tungsten. This is, let us say this is 3400 degree Celsius. So, that is equal to 3400 plus 273 Kelvin, that is equal to 36,273 Kelvin. Now, Tm W by 2 is 3673 by 2, that is equal to 18 and almost close to 1886.5 Kelvin. That is equal to 1886.5 minus 273, that is how much? 0.5316, 1613.5 degrees Celsius. You can't heat it up, right, beyond that. If you want to process by deformance processing, you have to go above this temperature. And tungsten has a BCC structure, so it is less ductile compared to many metals. So, therefore, we cannot have any choice other than powder processing. That is why powder metal is important. And powder process, actually waste of the material is very less. 97% of the powders are converted to compact, and PM products can be made with a specific level of porosity also. There are a lot of bearings which contains porosities, like self lubricating bearings in order to produce lubricants, like these are used in filters, oil impregnated bearings, gears, everywhere. So, powder metal allows you to produce that. Well, I do not want to go into details about glass stations, just to show you. This is the incandescent bulb and this is your tungsten coil. You see that this is a very intricate thing. We do not use incandescent bulbs now much because of the concept of fluorescent lamps, but still this technology was there for almost more than 100 years, and tungsten coils were produced by these powder metallurgy routes, remember this. And there are many other things like missiles, you have a piercing penetrators, and you need to use high melting temperature materials like tungsten based alloys, and they are mostly tungsten, 90% tungsten with some amount of nickel and iron to sinter, and they have very high density and dimensional tolerance. Well, there are many auto components are produced like these ones I shown you here by powder metallurgy. Many auto components are produced. Connecting rods can also be produced. Connecting rod example I have given in the last lecture. Gears can also be produced. Lot of medical radiation sealing machines, sealing components are produced. Okay, they are also made of tungsten heavy alloys or lead heavy alloys. Cutting tool inserts is a big industry worldwide. They are produced by these routes. So, how the PM material works? Mostly it is used for ceramic components. Metallic components also can be used as tungsten or other things, but there are components like copper, nickel, refractory metals, molybdenum, tungsten, and metal carbides such as tungsten carbides often included within the scope of this powder metallurgy. Well, I will not talk about powders much. Powders have definite morphology, like this is a mill powder which is irregular morphology. If you can produce powder by electrolytic grade also, copper which is a dendritic structure you can see here, and you can also have different ways of measuring the powder particle size like a skin mesh, and we talk about mesh, right, always in case of powder particle things. Shapes of the powder can be very different things. This is important when you talk about pressing and sintering, spherical, rounded, irregular, acicular, flaky, aggregate, spongy, different kinds of powder shapes are possible. Second, last important thing about powder is what? Angle of repose. When you put the powder on the surface, it will it will form a particular shape, and the angle is measured that way, shown here. So, this is also important characteristic when you put in the powder inside a die before pressing and sintering. That is what is shown here, and this actually depends on the interparticle friction and the flow characteristics. Now, I will not talk about powder productions because that is a big subject. Let us go to press and sinter. Once you have powder produced, the metallic powders are actually blended first. They blend or mixed together. After that, they are compacted, I showed you earlier, then sinter. So, what happens in compaction? Compaction is nothing but an application of high pressure, put the powder to form them into required shape, right. And I think I have a picture here shown here. So, you can see this is the mixing process. After that, powder is put into a die and then compacted. In compaction, you have to apply forces, you have to apply dye. It is done at room temperature normally, and after this, green pellet is produced. That is what is compaction is. There are different types of compactions presses available, single action, double actions. Okay, single action you can only use once. One punch is stationary, other punch is moving. Double action, both the punch is stationary. So you can apply force from both sides, but in the case of single punch, single action pressing instruments, the force is directly applied by top punch, indirectly applied by the bottom punch. In case of doubly applied punch, you apply force both the ways. So this is the advantage, and this is what is shown here. You see how this compaction is done. You can put powders, fill it the die, and after that you can push this punch by force. The force is very important parameter here, and then it will deform, or it will rather press the powders into a shape, and then you get a compact. This is very widely used, and this is what happens when you do the compaction. This is the loose powders. When you apply pressure, initially powders will try to pack nicely. If you apply more pressure, powder will deform, and that is why they can reduce these pores between the powders. But still, after pressing, some pores will live in, you cannot avoid it up. So that is why it is important to use sintering. Now in a single action press, since you are applying pressure from the top, there will be a variation of the porosities. At the bottom, porosity will be more, top porosity will be less. That is why it is better to use a double action press, and like this. Okay. In double action press, you are applying force both sides, so the powder will be compacted easily, nicely. There will be less number of pores on the both top and the bottom of the powders. And there are other kind of presses like isostatic pressing is also possible. Isostatic pressing is can be possible by using a liquid, and liquid can actually apply pressure from all the sides. Okay, that is why it is better compared to the single action, double action presses. The isostatic pressing is better because the pressure is uniform, so therefore porosities will be uniform inside the direction. So now the last thing actually which we will talk about is heat treatment or sintering actually. Sintering, heat treatment is sintering nothing but heat treatment, and it allows to form the bonds of the particles and thereby increasing this strength and hardness. What actually happens is that if you heat at high temperature, diffusional process will start happening. High temperature means between 70 to 90% of the metals melting point in the absolute scale, and it has been seen that the primary driving force for sintering is the reduction of the surface energy, total surface energy, because there are a lot of many particles. The particle will connect each other, and that is why they can reduce the surface energy, and this will also lead to reduction of sinkage during the this will lead to sinkage actually, and that is the way you can measure the pore size is getting reduced. And in a very layman point of view, this is a thermal treatment for bonding particles together into a coherent, predominantly solid structure by a mass transport or diffusion that occur largely at the atomic level, and bonding leads to improved strengths with a lower system energy. You can do either solid state sintering or liquid state sintering. In solid state sintering, you can basically do not use any liquid, it is simply a solid. Liquid sintering, you are using a liquid. There are two types of liquid sintering. One is called persistent liquid sintering, other is called transient liquid sintering. In persistent liquid sintering, you have lot of liquid present, like tungsten heavy alloy. You have a nickel and manganese, nickel and cobalt present. So nickel and cobalt mix together form a liquid alloy, and tungsten particles do not at all get melted down, because at the temperature of 1400 1500 Celsius temperature, tungsten, nothing happens to tungsten, and that is why actually they form a liquid meniscus around these particles, and then they can join easily after cooling it down. Or transient liquid sintering actually used for well pigmented bronze bearings like copper tin. They are actually use a very small amount of liquid is in a transient state. So how this sintering happens? Very simply, sintering happens by formation of neck. You can see that the points are connected, that is how the necks are forming, and the necks grow, and finally they join. In a very rudimentary way, this is how actually happens. Particle bonding initiated at the contact points grow and form a neck, then the neck grows, and they join together. And one can model it very different way using two particle things. If we use two particles, they are at the point their contact formation is happening, then this contact will lead to mass transport. Finally, they will join together by formation of a neck. You can clearly see there is a neck formation, right? This is the neck. Solid state sintering, this is how it happens. People have studied extensively. Formation of interparticle network or neck happens. This is a real picture of initial state and the final stage. This is an experiment using a spherical copper powder. You can clearly see there are mesh wires, and how these particles are forming necks. You can see there is a neck formation here. This is a neck, this is a neck, this is a neck, and the neck grows and form a nice compact. While liquid state sintering on the other hand is different. As I told you, there will be liquid phase. Here you see these are the solid particles, and you have a liquid particles which will melt down actually and form a liquid meniscus. Once the liquid meniscus forms, the particles will rearrange themselves nicely. In fact, liquid can fragment and penetrate also between the solid particles. So you can easily remove all kinds of porosities very easily. So you can see that finally it forms so many particles that can be joined together by liquid phase sintering. Tungsten hydrolysis has done that. More details of liquid phase sintering, you can see that there is a meniscus formation, this is the meniscus, and they are joined together. So you do not need to form a neck, you form a meniscus. This is a picture from our work on lead, copper lead alloy. Lead is a low melting temperature material, copper is a high melting temperature material relatively, and this lead actually act as a liquid phase during sintering at about 350 to 400 Celsius temperature. The copper can be easily sintered. Well, a bit of new processes which has been used for sintering. One is the spark plasma sintering. This is a snapshot view. In a spark plasma sintering, not only temperature or pressure but also use a current to increase the sintering rate, because this you can see these are the two electrodes in which the inside this dye and powder is kept. So if you apply low voltage, maybe current of the order of 500 to 1000 amps, that will pass through the powder and then allow further diffusion to happen because of the application of current. And this is widely used nowadays to produce sinter product at a very less time, and this facility exists at IIT Kanpur. This is a picture from our lab at IIT Kanpur, and this can allow you to prepare many compacts very easily. And in spark plasma sintering, there are two mechanisms exist formation. One is Joule heating. Obviously, if you have a lot of powders and pass huge current, what will happen is basically Joule heating, which is nothing but I square R T, right? Joule heating, heat is proportional to current square, resistance, and to time. And this heat can be heating up the contacts very fast and they can join. It can also lead to sparking, because if the current cannot pass through between the two contact particles, there will be huge sparking will happen, and sparking can lead to increase of temperature and mass transport. That is for electrically non-conductive materials. For conductive materials, Joule heating is the predominant thing happen. This is again from our work, tungsten carbide zirconium oxide. Tungsten carbide is basically a high temperature material which is used in the tool inserts. And as you can see, using zirconium oxide we can actually sinter them easily. These are the zirconium oxide particle between the large tungsten carbide particles. Okay, these are zirconium oxide particles. Here also you can see that. So tungsten carbide particle can be easily sintered using that in a spark plasma sintering unit. Well, one can also use selective laser sintering also. You can use powders, put it there, and then use a scan laser. You can actually melt partially, or incipient melting of this powder particle can happen, and they will then join together and form a nice bond, and then you can form a part. Okay. So there are many techniques available of sintering. So in a nutshell, I provide you a broad descriptions of this powder metallurgy processing in the last 25 minutes or so. But this is a subject altogether. If you want to study more, please look for books or the literature available on internet, and along with you can also find out some NPTEL lectures which are available. So with this, let us stop. So hopefully in the next lecture onwards we are going to start the statistical tools which are used for machine learning. And please remember this aspect, whatever I taught you for so last maybe 10 to 12 lectures will be very basic things which will be used for using machine learning models. So thank you for your attention.